Hey everybody, and welcome to our next video all about LeChatelier's principle. So we can talk about LeChatelier's principle because when we're talking about equilibrium, especially when we've been talking specifically about Q versus K, right? So sometimes Q is less than K, sometimes Q is greater than K. And depending on that value of Q is going to push the equilibrium either to make more reactants or we can make more products. And we can actually force a reaction that's in equilibrium to produce more or less product or reactant by stressing the system out, right? So if I were to add a little bit more reactant to a system, what is that going to do to my products? Or if I take away product, what is that going to do towards that reaction system? And we call that LeChatelier's principle. So if I disturb an equilibrium, or if I stress an equilibrium out, and typically that's done one of three ways. I could stress a reaction out. I could stress a reaction out by changing the temperature of the system. I could change the pressure of a system. And this is especially true with gases only, because pressure only affects gases. It really doesn't affect solids or liquids. Or I could stress a system out by increasing or decreasing the concentration of aqueous species. So if I change one of those three or more than one of those three things on a system that's already at equilibrium, that system is going to get stressed out. And it's going to try to relieve that stress somehow by shifting either to make more reactants or to make more products. So here's a great example of an equilibrium scenario. I don't want to say reaction because it's just dissolving in water. So I have CO2 gas that's in equilibrium with, I have CO2 aqueous, so it's dissolved in the solution. So I have this in a sealed container. So if it's in a sealed container, we could see that this is in fact at equilibrium because I have 1, 2, 3, 4 arrows going down. And I have 1, 2, 3, 4 arrows going up. So the number of those arrows is telling us that the rate at which the CO2 is becoming a gas, going from dissolved in the water to a gas, is equal to the rate at which the CO2 that's a gas gets forced back in to become dissolved. Those two rates are going at the same speed. And remember, we say that that's dynamic, right? So dynamic means that they're happening at the same time. Let's say, however, that I take this top part and I increase the pressure. So I apply some pressure to this top part, right? What's that going to do? That's going to stress the system out, right? Initially, it's going to stress it out. So what's going to happen is it's going to force some of that CO2 gas to go into the solution. It's going to force it to become dissolved. So it looks like I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 going down, and I have 1, 2, 3, 4 arrows facing up. So I'm not at equilibrium once I apply this stress because I have more going in one direction, right? But what happens is that this particular situation is going to relieve the stress somehow. So once it forces more CO2 to become dissolved, you could see in this picture, a new equilibrium is established after that. So again, I have 1, 2, 3, 4 arrows going down, and I have 4 arrows going up. So once I increase the pressure, that's going to decrease, or that's going to favor the side of the reaction with less moles of gas. Because if I increase the pressure, it doesn't want to be a gas anymore. It wants to go dissolved into the solution, right? So I have this equilibrium. I'm applying a stress and I'm forcing it to go in one direction, and I'm favoring the product side. of this reaction. I'm forcing more CO2 to become dissolved. And that's the whole basis behind LeChatelier's principle, is what's going to happen to the equilibrium? Am I going to form more reactants, or am I going to form more products based on this stress that I'm applying? So let's take a look at this particular example here. So I have some equilibrium. I have nitrogen and hydrogen. That's in equilibrium with ammonia. And I do have a thermochemical part to this. So in this case, this is some sort of heat. And heat is a product here. So because heat is a product, we call this an exothermic reaction. Those of you that have had Chem 2 will probably remember that. We're going to go back and talk about thermo in a little bit. After acids and bases, I'd like to do that. But this is what we call an exothermic reaction. Let's consider this reaction and say, what's going to happen to the concentration of everything if I apply some stress to this system? So this is in equilibrium with one another, going in both directions at the same time, at the same rate. Concentration of all my reactants and products are not changing. Let's say I add more nitrogen to this system. So my partial pressure of nitrogen is going up if I'm adding nitrogen. If I'm adding more nitrogen to this system, well, I have to produce more product, right? If there's more reactant that's there, it's going to force the reaction to go towards the products. So I'm going to also increase my partial pressure of ammonia. However, what does that do to my hydrogen? If I have more nitrogen that's there, and if it's going to make more product, that must mean that my hydrogen is going to have to react with it. So my concentration of hydrogen is going to go down. Okay, so if I'm adding more of one reactant, that other reactant is going to get used up more, but I can produce more product. And we could see here what happens to the partial pressure as a result of this stress right here. If I add more nitrogen, I can have a shift towards the products in this case. So instead of writing left, right, or none, we're going to write towards the products. I can produce more products if I add more reactant, right? That makes sense that that happens. What if I remove some hydrogen in this case? So I'm removing hydrogen. I already know I could decrease that right there. If I take hydrogen away, well, I can't produce as much ammonia from that, because if I don't have all that hydrogen, I'm not going to make as much ammonia. So my concentration of ammonia is going to go down. And if I have less hydrogen, that actually means my concentration of nitrogen will be higher. And that's because there's nothing for the nitrogen to react with. So because there's nothing for the nitrogen to react with, then of course that concentration or that partial pressure is going to be higher because there's more of it there. It's not being reacted with anything. In this case, if I'm taking away my hydrogen right here, if I'm removing some hydrogen, I can't make more products. Therefore, the reaction is going to shift toward the reactants. I am going to have a lot more nitrogen in this example because I can't form ammonia without hydrogen. So I'm going to have a lot of nitrogen sitting there. I always like to think of it this way, and it's a very silly example, but it actually works out great now that I have a 3-year-old at home. If you give a 3-year-old something, so let's say this right here is my Natalie, right here, N for Natalie. I give her something, right? Here, Natalie, take this banana. What does she want? She doesn't want the banana. She wants something else, right? So if I give something to her, she wants the other thing. So the shift is going to be towards the other side of the reaction. She says, no, mommy, I don't want that. I want this, right? So it shifts the opposite way. Even if I say that this is Natalie, here, Natalie, you take this, right? I'm giving this to you. No, mommy, I want this, right? It shifts in the opposite direction. Let's say I take something away from her. I say, no, Natalie, you can't have that. That's bad, right? No, Natalie, you can't have an ice pop right now. It's, 9 o'clock in the morning, and I take it away. What does she want? She wants that thing, right? So if I take it away, that's what she wants. So if I take something away from the reactant side, this reaction is going to shift towards the reactants, okay? Very, not as complicated of an explanation, but I do like to usually use that when I talk about equilibrium. In the same sense, if I'm adding ammonia, so here we go, I'm adding ammonia, right? Of course, my partial pressure of ammonia is going to go up. And if I add more ammonia, that's going to decompose and produce more nitrogen and hydrogen. So both of those will also increase. If I'm adding more ammonia, I give something to Natalie, she wants the other thing. So my shift is going to be towards the reactants. I can make more reactants because I have more products available. There is more ammonia that's going to decompose. So therefore, more of those reactants are going to form. Let's take a look at temperature. So temperature is a form of heat, right? And I like to think of this, especially because we didn't talk too much about thermodynamics yet. I like to think of this heat as an actual reactant or product, because technically it is, right? If I have nitrogen and hydrogen, that's in equilibrium with ammonia, but I'm also producing heat in this case. If I increase the temperature, so this is the same thing. If I increase the temperature of the system, ammonia and heat very readily react together to form more of this. So if I apply more heat to this side, that's going to force NH3 to decompose, right? Because ammonia decomposes when heat is there. So in this case, if I add heat to the system, I'm going to have a shift towards the reactants. So therefore, if that heat reacts with that ammonia, that concentration of ammonia is going to go down, and I'm going to increase the partial pressure of both of those two reactants at the beginning. So more heat when applied to NH3 is going to produce more of these. Now remember, this is all in equilibrium. So all of these are present at one point in the reaction vessel. So that's why I can immediately go to this side and say, okay, well, that whatever ammonia is there is going to decompose as a result of that heat. Let's say I decrease the pressure. Remember, pressure is only affected by gases, or gases are only affected by pressure. So in this case, I do have gases in this example, so this will work out. On my reactant side, I have 1 nitrogen and 3 hydrogens. So that means I have 4 moles of gases present on my reactant side. On my product side, however, I have 2 moles of gases. The side that's favored with a decrease of pressure, right, the lower the pressure, is going to favor the higher volume. If I think about Boyle's law, right, Boyle's law was P1V1 equals P2V2. So if the pressure of a system is going to go down, that means that the volume is going to go up, right? So when I decrease the pressure, we want the side of the reaction that takes up more volume. We'll say takes more V for volume. Which side of these favors the one with more volume? Well, the side with more particles, right? So in this case, again, because you have 4 moles of gases on your reactant side and 2 moles on your product side, the side that's favored is the one with more particles of gases. So again, we're going to favor the reactants here. So therefore, my concentration of both of these are going to go up, and my concentration of ammonia is going to go down. Same thing if I decrease the volume of the container. Now, volume in particular, we can't think of it in terms of volume, but again, if we think of Boyle's law, the lower the volume of a container means the higher the pressure would be in that container. So in this case, the lower volume is going to mean that we have an increased pressure in that system, increased pressure. The higher pressure means that the side of the reaction that's favored is the side with lower number of moles of gas, right? Because we want less actual particles that are there and higher pressure. So this particular reaction is going to shift toward the products. I'm going to produce more ammonia, and I'm going to use up all of that nitrogen and hydrogen. Even though the ammonia particles are larger, it doesn't matter. There's less particles that are there. And the less particles there are means the lower the pressure is going to be. So lower pressure, or we'll say higher pressure, higher P, always favors less moles of gas. Higher pressure will always favor less moles of gas. So let's take a look at sample problem 14 in this case. Looks like we're still working with gases here, except notice that my heat is on my reactant side of this equation. So we call this an endothermic reaction. So we're going to, by writing, instead of left, right, or none, again, we're going to write products or reactants, and we're going to say what's going to happen to the concentration of each of these. So if I'm adding iodine, right, of course my concentration of iodine is going to go up. If my concentration of iodine is going to go up, well, I could produce more hydrogen iodide, that is. If I give Natalie this, she wants this, other side of the equation. So we can, in fact, increase the partial pressure of hydrogen iodide. However, if I'm given more iodine, more hydrogen is going to react with that. So in this case, your partial pressure of hydrogen is going to decrease. If you have more iodine, more hydrogen has to react with that. So that's going to decrease. Therefore, my shift, if I have more iodine, is going to shift toward the products. I'm just going to write P. Oh, I'll write the whole thing, I guess. Shifts toward the products. Let's say I remove some HI, right? I take some of this hydrogen iodide away. I take something away from Natalie. What does she want? That thing. So I would have a shift toward the products. If I take HI away, the reaction is going to force itself to make more HI in order to reestablish equilibrium, in order to keep that equilibrium constant. So, and actually, if I decrease the concentration of this, right? So if I consider my equilibrium expression, HI squared over H2 over I2, if this concentration goes down, right, what does that do to Q? That means I have a low value of Q. That Q is less than K. And if Q is less than K, well, that means it has to make more of those products in order to reach equilibrium. So it kind of all comes together when we talk about Q and K and LeChatelier and these shifts and equilibrium, and it all starts to come together. If I remove HI, well, that's going to go down. And if I take that away, like we said, more hydrogen and iodine have to come together to make more HI. So in that case, both of these concentrations are going to go down. Remember, let's think of heat or temperature as an actual reactant in this case. I think it's easier that way. In order for hydrogen and iodine to synthesize and form hydrogen iodide, heat's necessary for that. Think of it like cooking an egg. You have an egg on the stove. You need heat to make a scrambled egg, right? If I increase the temperature, I can make that scrambled egg, right? Whereas if I take temperature away, or if I don't heat it up at all, I'm not going to make the scrambled egg. So it's going to stay on one side of the reaction. If I increase the temperature, I could force this reaction to make more hydrogen iodide. So I would have a shift toward the products again. What does that mean? If I increase the temperature, more of these are going to react with that, or react with one another to produce more hydrogen iodide. If I increase the pressure, so we do have to look at number of moles of gases on both sides. So Looks like here I have 1 mole of hydrogen and 1 mole of iodine. So that's 2 moles there. And actually I have 2 moles of products that are gases as well. Because I have the same number of moles of gases on both sides, if I increase the pressure, there's going to be no change. Right there. Pressure does not affect this particular system, and that's because if I increase the pressure, neither side of the reaction has less particles. So it's kind of like, okay, well, it doesn't really force me to do anything because if you increase the pressure, I have the same number of particles on the other side. So what's the deal, right? It doesn't make a difference in that case. So increasing the pressure in this example will have no change, and that's because your number of moles of gases on reactants and product side are the same. Here there was an effect because I had 4 moles of gases relative to 2 moles of gases on the other side. The higher the pressure favors the less moles of gas. In this case, we didn't have that. Here's an example that kind of goes back to kinetics, and I know I didn't teach kinetics yet, but a catalyst is something that we haven't talked about yet. And a catalyst speeds up a reaction. A great example of a catalyst is actually Mentos and soda. So when you put Mentos and soda, as we know, that soda comes flying out of the top. Why does that happen? That little Mentos has a whole bunch of ridges on the surface, and that CO2 that's inside of the soda is able to form bubbles on that surface, and when they form bubbles, they come shooting out of the top. So it just makes the soda go flat faster, actually. And that's what we call a catalyst. It speeds it up. So if you have a liter of soda sitting on a table with the cap off, it's going to go flat eventually. But if you add a Mentos to that, it makes it go flat much faster. So it just speeds it up. So in this case, it says, what effect would adding a catalyst have to this equilibrium? Well, in fact, we've already said that equilibrium is really independent on rate, of course, until we get to this point where the rates of the forward and reverse reaction are the same. Otherwise, it doesn't matter how long it takes to get to equilibrium. It will still reach an equilibrium, right? So if I add a catalyst, if I speed up this reaction, there's also going to be no change. Catalysts don't change the equilibrium at all. They just allow a reaction to reach equilibrium faster, right? It allows the rate of the forward reaction and the rate of the reverse reaction to equal one another much quicker than it would without that. So adding a catalyst, there's always no change to an equilibrium, just makes it happen a little bit faster. Last one, let's talk about 15 here. So 15, this is a dissolution a dissolution process. Dissolution. So we could see I have solid sodium hydroxide dissociating into sodium ions and hydroxide ions. This is an exothermic reaction. I do have a little bit of heat here that comes from that. When I have a dissolution reaction or a dissociation reaction, this must mean that this particular solution must be saturated. And if you think back to Chem 2, a saturated solution is when you have a particular material that is dissolved to the max, right? I can't have any more solid that's dissolved. It's reached its dissolving point. So once it's reached its dissolving point, you're going to have a little bit of solid left here on the bottom. And the rate at which this particular crystal is dissociating into the solution is equal to the rate at which it's precipitating back on. So that's why we say that even dissolving is an example of an equilibrium, but only if it's a saturated solution, right? If I had a beaker with nothing in it, right, that means that all of the salt or all of the whatever has dissolved. So the rate at which it's dissolving is greater than the rate at which it's precipitating. So if I have a solution with nothing sitting at the bottom that is not in equilibrium, I have to have some sort of solid hanging out down there because some of these dissolved particles have to precipitate back onto the crystal. We talked about that a little bit in Chem 2. So let's see, considering this, if I add sodium hydroxide to a saturated solution, okay, I'm adding solid sodium hydroxide. I have this reaction, or I have this beaker that's already maxed out with how much it can dissolve. If I add more sodium hydroxide, I can't make more product because it's already maxed out, right? I can't dissolve more sodium hydroxide in this saturated solution because it's already met its equilibrium. And we notice that this is a solid. So in this case, adding sodium hydroxide has no shift. There's no change here, right? And that's why solids are not affected, is because if I add more solid, well, it's not going to force sodium hydroxide to become more soluble. It's already maxed out. So in that case, there is no shift in that case. This should also be amount of. We really can't have concentration of NaOH because it's not aqueous. So it's just amount of sodium hydroxide. Let's say if I add a little bit of salt to this, right? And we know salt dissociates very well. So salt is a source of sodium ions. So if I add some salt and therefore I'm adding sodium ions, the more sodium ions I have, right, the more sodium hydroxide solid I can produce, right? The reason why this is affected is because I could change the concentration of an aqueous species. This I cannot change the concentration of, but this I can. So if I'm adding some sodium ions, I can make more solid sodium hydroxide. And we're going to talk about this later when we talk about solubility and the common ion effect. We could force something to precipitate more by adding what's known as a common ion. And that's what this is right here. This is a common ion. So salt has Na in it, and so does this reaction. This means that I'm going to use up more hydroxide. If I add more sodium, my concentration of this has to go down. And I'm going to have a shift toward the reactants. I can make more precipitate by adding more sodium ions. So if I look at hydrochloric acid is a source of hydrogen ions, which, as we know, if we think back to strong acids and bases, sodium hydroxide is a strong base. Hydrochloric acid is a strong acid. We're actually going to add protons, and we are going to take away hydroxides in order to form water. Strong acids and strong bases, as we know, form water. So adding hydrochloric acid is actually decreasing my amount of the hydroxide ion. And that's because they're going to come together to form water. If I'm decreasing my amount of concentration of hydroxide, I can't precipitate as much sodium hydroxide from this. And as a result, my sodium ions can't react with anything. So that concentration will increase. If I take some hydroxide away, I'm going to have a shift towards the products. More sodium hydroxide is going to dissociate and try to make more hydroxide to make up for that loss. So in this case, I'd have a shift toward the products. Let's say I have an increase of temperature. Like we said, here's my temperature, heat it up. I can actually form more sodium hydroxide in this case. So I would have a shift toward the reactants. Therefore, I would have an increase, a decrease, and a decrease. If I add heat, that's going to force sodium ions and hydroxide ions to come together and make more solid sodium hydroxide. Last one, let's look at the pressure. I have a solid and an aqueous species and another aqueous species. I have no gases in this case. Because I have no gases, there is no change or no shift based on this. Pressure does not, a change in pressure does not affect solutions. And that's because no matter what the volume is, the volume's not going to change because the particles are already packed pretty closely with one another. This is an interesting topic, right? And we're really bringing all of this equilibrium stuff together. I feel like at this point, we can really tackle some pretty good equilibrium questions at this point, which is what we're going to do. As always, if you have any questions, please make sure you ask me. As you know, we will do more practice with this in class. Otherwise, we're almost done with equilibrium. In the next video, we're going to talk more about the solubility product constant, so more so about this right here and how much something dissociates in solution. And then we'll talk about that common ion effect, like I said, too. So, otherwise, I will see you in the next video all about those things, and I hope you have a wonderful day. Bye.